In this lesson, we're going to learn what's probably the most important derivative rule there is. It's called the chain rule. We'll explain why it's called the chain rule as we go. And there'll be two different notations that you're going to want to observe and be comfortable with by the end of the video. Okay, before we get into the chain rule and what it does, let's review what a composition of two functions is from pre-cal. So let's say that f of x is sine of x and g of x is x squared. Okay, what is meant by f of g of x? Well, this is intending to mean let's input the function g of x into f. Okay, and so what happens as a result of that? Well, this means replace the input of f with g of x. So it would look something like this. Since f is the sine of x, I would say I have the sine of whatever g of x is, and g of x is x squared. So a composition is a function input into another function. Similarly, g of f would be take the function x squared and replace the input with whatever f of x is. In this case, f of x is the sine of x. And you can even compose a function with itself. F of x means take your function f and input itself into itself. So in this case, you'd have the sine of the sine of x, and g of g would mean take x squared and input itself into it, x squared. Sometimes you can simplify a composition of two functions. For example, x squared can be rewritten as x to the fourth, and that just looks like a run-of-the-mill everyday function. But the rest of these you can clearly tell are compositions, function input into another function. Now let's take a look at why we actually need a rule that deals with compositions of two functions. Here's an example of what's clearly a composition where we have the function 2x plus 1 as an input into the function x squared. We end up with this function right here. Now, it'd be very nice if we didn't have to worry about anything and we could just treat this as something squared, in which case we would say, okay, then the derivative of y is going to be 2 times that thing that's being squared to the first power, and we'd be done. In other words, I'm just using the power rule on this function because this is some function being squared. Okay, if we simplify this, we would get 4x plus 2, and that's a legitimate approach to this problem for the first time you see it. Now, we also know that you could expand this function in this case and get 4x squared plus 4x plus 1. And now we will surely get the answer that's correct by taking the derivative, because these are just three power functions. And so we will get 8x plus 4. Now, these are not the same answer. So clearly, this is not correct. But this 4x plus 2 function is related somehow to 8x plus 4. Okay? You may see that if I multiply this by 2, then I would get the correct answer. And then the question is, well, what does this 2 have to do with 2x plus 1? In other words, how would I know that I needed to multiply by 2? That's what we're about to take a look at with the chain rule. So here's what the chain rule says. All right, and this is symbolic in function notation. It says the derivative of f of g of x, in other words, the derivative of a composition of two functions, is equal to the derivative of f at the original input g. So that the input did not change. That's not enough, though. You also have to multiply by the derivative of that input g of x. We call it the chain rule because we're tacking on an extra derivative to the end of our answer, kind of like a chain. And if there's multiple functions being input, you'll see multiple links in the chain. So if we went back to this example right here, we could have approached the problem in this first manner. Take the derivative of the outer function, which is the squaring function, which is 2 times that number to the first, but then you needed to multiply by the derivative of the inner function. So I needed to multiply this by the derivative of 2x plus 1, and that's where that 2 came from. It was the derivative of the inner function. So in cases where I cannot expand and do it in this manner, I will do it using the chain rule over here, and sometimes it's impossible to do anything but use the chain rule. So that's why this rule is so important. You're going to use it the most probably out of any. Now, this is all good in symbols, but in practice, until we get the hang of it, we sometimes like to use some abbreviations or some substitutions that make sense to us. So I like to do this. I say, okay, if I have the derivative of f of stuff, okay, how do I do this? And this is what I think makes sense to students in the beginning here. Okay, what do we do? The derivative of f of stuff is f primed of stuff. So I'm saying there is that stuff does not change when I take the first derivative. And then I need to multiply f prime of stuff times the derivative of the stuff. And sometimes there'll be multiple things, okay, so stuff and then stuff part 2 that I need to take the derivative of, and you'll see some examples as we go. Okay, so this is just kind of for your reference and to get the hang of it. Eventually you'll get used to this notation up here. Alright, let's jump into some examples. I'm going to get a lot of examples today. So if I look at this function here, this is, in my mind, like e to the stuff, okay, the stuff being x squared. So it's clearly a composition of functions. I need to use the chain rule, okay. So the chain rule says take the derivative of the outer function, so it's e to the stuff, and the derivative of e to the stuff is itself, right, e to the stuff. So e to the x squared. And then the chain rule says you need to multiply by the derivative of the stuff, so the derivative of x squared. So my final answer is going to be the derivative of this y that we started with is e to the x squared times 2x. The derivative of the outer function, which is the e function, and times the derivative of the inner function, which is the x squared function. Okay, where is my inner function and where's my outer function in this case? Well, if I rewrite it, it'll be more clear. So this is the same as saying y equals quantity sine x squared. So again, in this case, or not again, it's a little bit different here. In this case, the outer function is the squaring function. So I know how to handle that. The derivative of something squared is 2 times that something to the first power. Okay, that's not enough because this is a composition of functions. So I also have to multiply by the derivative of the inner function, the derivative of the stuff. In this case, the derivative of sine x. And so my final answer here is going to be 2 times sine x times cosine x. This looks similar, but it's a little bit different. This time the outer function is the sine function, and the inner function is the squaring function. So I'll do the same operations, just in a different order this time. So I have the derivative of sine is cosine. So I'm going to have the cosine of x squared times the derivative of x squared. And eventually you will not write this intermediate step that I'm writing. You'll just do it mentally. But in the beginning, it's good to show your work and see where you might have made a mistake if you forgot something. So we have the cosine of x squared times the derivative of x squared, which is 2x. Now, look at this problem here. This could, in theory, be expanded. It's 3x plus 2 to the 10th. So it's 3x plus 2 times itself 10 times. So you could create a bunch of power functions and then take the derivative. But the expansion would not be a lot of fun to do. This is where you really appreciate the chain rule, because now it says, hey, you have something to the 10th power. That means the derivative is going to be 10 times that something to the 9th. But you must also multiply by the derivative of the inner function, in this case 3x plus 2. If it was just x to the 10th, you'd be done. It'd be 10x to the 9th to be finished. But this is a function besides x, so we have to account for its derivative as well. So we will finish with 10 times 3x plus 2 to the 9th times 3. And yes, you can multiply the 3 and the 10. And that simplifying is some work you'll be needing to do eventually. For now, we're just getting the concept here. Alright, now this one is kind of loaded. We got a bunch of stuff going on here. Who is the outer function, the outermost function in this case? Well, it's the square root. And the rule I have for square roots is to make the square root into a half power. So let's go ahead and rewrite that. Sine of 2x is inside. This is a 1/2 power. So using the power rule, I will write g prime of x is equal to 1/2 times that whole quantity untouched, to the negative 1/2. That's the power rule. It says bring the exponent down in front and subtract 1 from the exponent. And now I need to multiply by the derivative of the inside. So let me scoot this over a little bit so I have some room. Now, the derivative of the inner function, which is really two functions put together here. So what are we going to do here? The derivative of cosine x plus sine 2x. All right, let's go ahead and take care of that, and then I'll just bring that other part down in a second here. The derivative of cosine x is negative sine x from the other day in class, and then the derivative of the derivative of sine is a cosine. So I have cosine of 2x, and then I notice, oh, I have to use the chain rule on the 2x also. So times a 2, the derivative of 2x. Okay, and then this portion right here we'll just bring on down. A lot of simplifying that could be done here, and as you can see, these problems can get quite complex. And here are examples where you have three functions being composed. In this case, the x squared function is input into the sine function, and then that sine function is input into the tangent function. So now we have a outer function, tangent, a middle function, sine, and a inner function, x squared. So how am I going to handle this? Well, we start with the outer function. What is the derivative of tangent of stuff? Well, secant squared is the derivative of tangent. The input remains the same. So I have secant squared of the sine of x squared. Now we start tacking on derivatives, okay? Times the derivative of sine of x squared is going to be the cosine of x squared. And now x squared is my inner function. I need to multiply by the derivative of x squared, which is 2x. Okay? If that went too fast, then take your time and write it out. I'll write it out on the next one a little bit slower so you can see all the steps. Now, in this case, I have to look at the bigger picture here. What's going on here? I have e to the 2x times the sine of 3x. So in the big picture, this is a product. So the product rule is in effect. So let's label my pieces here. My u function is e to the 2x, and my v function is the sine of 3x. So my u primed function is going to be e to the 2x times the derivative of 2x, which is 2. And my v prime function is going to be the derivative of sine, so cosine, of 3x times the derivative of 3x, which is 3. So now I'm ready to write what y primed is. Okay, so remember that the product rule is v u primed plus u v primed. VUV. Alright, so my v is the sine of 3x. My u primed is 2 e to the 2x. Addition, right? My u function is e to the 2x, and my v prime function is 3 cosine of 3x. So two examples of, well, one example of a triple composition, and then here's a product rule with a chain rule used in the middle of the process here. Okay, this is a little different notation. This is the differential notation in German, and you need to recognize both types of notations, not just the f of g, but also what I'm about to show you here. So if you're asked to differentiate y equals tangent of x cubed plus x, that means in differential notation, find dy over dx. That's the symbol for the derivative of y using differential notation. Now, what's common in pre-cal, and will be common in calculus as well, is to make substitutions to make our problems a little bit simpler to look at. So a common substitution is a u substitution, where we say, okay, let's replace x cubed plus x with the letter u. Okay? So now you would have y equals tangent of u. And at this point, we can do a derivative, but the derivative we find would not be dy over dx because x is not the independent variable in this picture. The independent variable is u. So the derivative I'd be finding is dy du, and that would be equal to secant squared of u. Now our goal was to find dy over dx. And if I think of this as a fraction, technically it's not, but if I do think of this as a fraction, then I would need to multiply dy du by something to get dy dx. Okay, I would need to have a dx in the bottom, the denominator, and I would need this du to get canceled out, so I would need to multiply by a du in the numerator. Well, if I do that in the numerator, or sorry, on the left side, I need to also do that on the right side. And so now I can look at this as being two fractions, and the du's would cancel, and I would get my desired derivative, which is dy dx. Now I need to figure out what is du dx, and I go back up here to where I have u to find in terms of x. So here I would say, all right, du dx is equal to 3x cubed plus 1. And so my final answer here would be secant squared, replace my u, which was x cubed plus x, times 3x squared. This should have been a squared up here. There we go. 3x squared plus 1. So this is the differential notation that you're going to get used to. It says that if you have dy over du times du over dx, that becomes dy dx. That's another way to present the chain rule.